everybody, Mr. Covey here, and thank you for tuning into the second half of our Chapter 6, Chapter 7 video here. And I'm going to be talking about differential equations, and then related to differential equations, slope fields, Euler's method, and logistic growth. So if you remember at a most basic level, what a differential equation is an equation that has a derivative in it. Okay, that's what a differential equation is. Solving differential equations is a huge topic. You guys will all take a class on it in college because you're going to study math or engineering. But for our purposes, we only learned one technique to solve differential equations, and it was called separation of variables. Okay, we'll talk about that. It's very important that you know that one technique. Okay, a big mistake that a lot of you guys made on this test or quiz, I can't remember, is there was the whole issue of like, where do you put the plus c when you do the separation of variables? And you're supposed to put it as soon as you integrate, you put the plus c. And the other thing connected to that is if you are solving for the plus c by plugging in a point, you should plug in that point as soon as you integrate. Okay, and there was some issues with that, so we'll go over that. Cool. Oh yeah, that's just a little summary of that idea. Cool. Okay. All right, so differential equations. First, before we even talk about solving differential equations, we talked about a slope field. So a slope field was not a way to solve a differential equation. It was a way to visualize solutions. Hopefully you have that thing in your calculator that makes slope fields. But remember, it's just a way to visualize what solutions to a differential equation like this would look like. This is an example of a differential equation where we can't separate the variables. You guys don't know how to solve this. They could ask you to do stuff with this in an AP problem, though. Very realistically, they could. And one of the things they could ask you to do is make a slope field. Here's a reminder what slope fields look like. Okay, I just made that slope field for dy dx equals x plus y. As you can see here, at each x value, you plug in the x, or excuse me, at each point, you plug in the x and the y value into the derivative, and it tells you the slope, and you make a little tangent line with that slope. And you can kind of trace a solution. So if you knew a solution went through 2, 3, you kind of hop around here and see what that solution would look like. Okay. Another thing we learned about differential equations that we can't solve is we learned how to use something called Euler's method. You remember the thing from Hidden Figures? She's like, I'll use Euler's method. Yeah, that thing. Okay, so our advice, this is not like the official way to do it, but our advice that is really helpful, Lemke's advice, is to make this chart that we told you about when you see Euler's method. So you need to remember that the chart has your x and your y, your derivative at that point, and then what you try and figure out is your delta y. As you're trying to figure out how much to increase the y by. How do you do that? Well, you do dy dx times dx because the dx's cancel and you figure out dy. Okay, so for this technique, you have a differential equation. Okay, they give you a starting point. They ask you to predict the y value at another x value. And then they might tell you how many steps to do, or they might tell you the size of each step. In this case, they're telling us the size of each step. So they're saying, hey, start at the 0.35, do steps of 0.5 x values, and do that until you can estimate the y value and x value of 5. Okay, so then that's just a matter of knowing how this chart works, and it's really easy. If you remember these headings on the chart, it's all about like knowing these headings, and this thing just like kind of fills itself out. You toss down the point, there's x, there's y. Here's our differential equation. This is the one we're going to use for this Euler's method table. All right, so dy dx equals x plus y. So dy dx equals 8. What is dy? Well, it's dy dx times dx, okay? Our dx here is 0.5. Each step is going to be 0.5, and that gives us our change in y. So our change in y here is 4. Sometimes it's helpful right at the beginning if you know the dx thing, which you always do. It's just to be like, oh, so I'm going to do a step to 3.5, a step to 4, a step to 4.5, and a step to 5. Okay? I'll fill out one more line, and then we can kind of fast forward. Okay. So now I know my dy. So what's my new y? Well, it's 5 plus my dy, so it's now 9. What's dy dx? Well, it's 12.5. It's x plus y. Again, I want to emphasize this. The reason we're doing x plus y is because that's what the differential equation says. dy dx equals x plus y. If it said 3x plus 12y, then we'd do 3 times x plus 12. It depends on what the differential equation says. Okay, so now we know dy dx. dy dx times dx gives us dy. 6.25 is dy. So now what's my new y? It's 15.25. Okay, you can pause and finish this up. Cool. Okay, that's what I got there. And I can stop right there, notice, because all I was trying to figure out was what y value goes with an x value of 5. And so based on this Euler's method, y value of 39.5625 would go with it. Cool. Okay, a couple other things about differential equations. There's 2 differential equations that you should recognize. The first is when you come up to a differential equation, it says dy dx or dy dt equals number times y. Okay. In other words, the derivative is the same as the original function, or it's a multiple of the original function. What type of function has its derivative is the same as itself? Exponential functions, or exponential functions with a little constant there. Okay. The rate of change in these is proportional to the function. Okay. Again, if you don't know this, you can solve this differential equation by separating the variables and integrating both sides. Okay, but it is kind of cool just to know that, like, that jumps right to that. This is the solution to this differential equation. The other type of differential equation we looked at was this logistic growth. Okay, this one you guys didn't like this. I know this was confusing. But basically the idea was, if you stumbled across a differential equation that looked like this, or that you could do algebra to make look like that, then its solution was a logistic growth function that looked like this. Okay, I'll say that one more time. If you came across a differential equation that looks like this, or that you could make look like that, then the solution to that differential equation was a logistic growth function that looked like that. Okay, logistic growth functions are important because, remember, they're kind of like exponential, but then they're realistic. They're much more realistic than exponential growth, because there's a carrying capacity, there's a maximum. Okay, so you reach this point, and then it doesn't just keep growing exponentially forever. It starts to level off. Okay. You probably noticed a lot in the news now. They've been talking all about exponential growth with all the COVID stuff, and it's been really interesting to think about a lot of the calculus stuff. You know, take a little break from all the seriousness and just kind of think about the calculus and be like, this point of inflection here is like a good example of, like, people have been talking about, like, the rate of change is still positive, but they're trying to figure out when the rate of change is peaking. In other words, they're trying to find the maximum rate of change. In other words, they're trying to find the point of inflection. And you don't hear those words because people don't like calculus words, but that's what they're talking about. They're talking about when does the rate of change maximize. In other words, when do you have a point of inflection? Okay, it's all math. It's cool. Anyway, back to logistic growth. Remember, y equals L in this function. L is your carrying capacity. It's that horizontal asymptote. It's that maximum. B was the kind of the random constant that is the plus C in the logistic growth one. And the K is this K. Cool. Your point of inflection happened halfway to your carrying capacity. Okay, so that's a little shortcut there. The one reminder I wanted to give you about this was, hey, if you forgot this top one, and you forgot that this differential equation has this solution, no worries, just separate the variables. If you forgot that this differential equation has this solution, you're in bad shape, because remember, like, actually separating the variables and solving that differential equation is extremely tedious. I struggled through it in class. Remember, I got all messed up and stuff because it's really hard to do. So you should know that. Okay. And final reminder I'll say about this is a lot of times your logistic growth differential equation won't look like that. It'll look more like this. And what you need to recognize is if it has a linear part and a quadratic part, and you can GCF out the y, and in this case the 5y, to make it look like that. So you could do this little GCF in here, and now this looks like this, and you could look at that and say, oh, the carrying capacity is 5/3 and k is 5, and you can kind of go like that. Okay, linear part, quadratic part. Okay. Alrighty, I want to. Oh yeah, we got to talk about the memes, and then actually going to do an AP question. So you know how Miss Lemke talked about that banana problem? Well, there's another kind of famous AP problem relating to this baked potato. And there's always funny memes like my baked potato was too hot and stuff like that. But just like the banana problem is kind of like a classic flow in, flow out problem. Like when we see me and Mrs. Lemke, I don't know if Miss Lemke really said this, but when me and Miss Lemke like saw a problem like the banana problem, we're like, oh sweet, our kids know how to do something like that because it's kind of a traditional problem that we prepared you for. This baked potato problem, another classic problem. Okay, Mrs. Lemke was traumatized by this. She didn't eat a baked potato for like a year and a half afterwards. Anyway, all right. So let's take a second to kind of read the STEM. And this was a shared question between AB and BC, so you know some of them are AB only. This is a harder question because it was also appropriate for the BC exam. So let's read the STEM, and then we're going to go through these different parts here. Cool? Okay. So time t equals 0, baked potato, boiled potato, whatever. Left to cool in the kitchen. Okay, it's taken out of the water. 91 degrees Celsius at time t equals 0. And by the way, the temperature stays greater than 27 the whole time. The internal temperature is modeled by this differential equation. H of T is heat, measured in Celsius, and they again are re-emphasizing that initial condition, it was initially 91 degrees Celsius. Okay. I think we should just walk through all these together. But my number one warning at the beginning is when you see a differential equation, don't solve it. Like, don't just like, you guys are so like trained to just like see an equation and start trying to solve it. Read the question, see if they even ask us to solve it. It's possible they won't even ask us to solve it because we either can't or they just don't even want us to. Okay, so let's go through these different parts here. First thing, they're saying, hey, write the equation for a tangent line to h at t equals 0. Okay, and then use this equation, this tangent line equation, to approximate the internal temperature at times t equals 3. Awesome. Equation of a tangent line, I need a point, and I need a slope. Okay, you guys know this. T equals 0, they give me that point. I have a point is 0, 91, my t and my h. And I need a slope. Oh, I can give the derivative right there. Please be careful. What I'm plugging in here is h, so I'm plugging in 91, negative 1/4, times 91 minus 27. Okay, so I get negative 16. I have a point and a slope, equation of change line. Y minus y1 equals m times x minus x1. I guess here I should use t and h. Come on, Mr. Okay. Cool. I have an equation of a tangent line. Second little part says, oh, now that you have this equation of tangent line, use it to predict the internal temperature at time t equals 3. Toss in 3 for t. (43°C). Make sure we toss down the units to show that we know what's going on. Cool. Okay. Part A, again, we didn't solve the differential equation. We just wrote the equation of a tangent line. Very typical question. All right. Question B. Use d squared h t squared to determine, second derivative there, determine whether your answer in part A is an over or under estimate of the internal temperature. We asked you guys this question for a semester like 68 times. Me and Mrs. Lemke got in big fights about this. She'd be like, let's ask them that question again. I'd be like, Miss Lemke, we've asked them that question like 19 times. She'd be like, we should ask him it one more time. I'd be like, fine. And then somehow you guys would still get it wrong. And I'd be like, we've asked this question a bunch of times. Okay. So remember, this question is talking about whether a tangent line over or under approximates. Okay. Well, yeah, let's just talk about the picture now. So remember, if you have a tangent line, your over or under approximation of a curve doesn't depend on whether it's increasing or decreasing, depends on concavity. So if your function is concave down, then your tangent line over approximates. See how it's above your function? If your function is concave down, concave up, then your tangent line over approximates. Again, this is not something I memorized. This is just something I understand by drawing these little pictures. Okay, so this is a question related to that. So first, we got to find the second derivative. Okay, please be really, really careful here. This was, again, I'm having a flashback to when we had a test quiz on this, and you guys, a lot of you guys made this same mistake, which was you got confused here, and you said, oh, I'm doing a d squared dht, and you said it's a negative 1/4. The thing you were getting confused about was the variables. So remember, like, step back for a second. This is like, if you think about it with y's and x's, this is dy dx equals blah, blah, blah with a y in there. Uh-oh. dy dx has y's. This is more complicated. Like, I'm finding the second derivative and my dy dx has y's in it. If my dy dx had x's in it, then I just do normal derivative rules. But it has y's in it, so I need to do implicit differentiation. Okay, your derivative isn't just in terms of this lower variable. It's not just t's over here. I got an h in there. It means I need to do implicit. Okay, so what's the derivative? Well, the derivative, you know, if you want to distribute, you can. Now I'm going to do the derivative. What's the derivative of negative 1/4 h? Negative 1/4 dh dt. And again, because I'm not differentiating with respect to h, I'm differentiating with respect to t. Okay, so here's where I'm at. But you're like, negative 1/4 dh. Oh, remember dht is just that thing up there. So I'm going to take this whole guy, and I'm going to sub it in there. You with me? Okay, so I'm going to get positive 1/16 h minus 27. That is the second derivative of h with respect to time. Okay. I know what you're thinking now. You're like, okay, cool. So now I'm going to find the concavity. Wait, what should I plug in for h? Should I plug in like that starting h or the one that I predicted, or doesn't matter? They tell you one thing here that's kind of annoying. In the very original question stem, they say this. You're like, that's a weird thing to say. They're saying that so that you can come down here and say, look, the hot potato is over 27 degrees. So the second derivative, if h is greater than 27, this is going to be positive, right? Put that there. Like, right, the h minus 27 is going to be greater than 0, and 1/16 times something greater than 0 is going to be greater than 0. Okay, so since this is true, then this is going to be true for all t. So it doesn't really matter. Our second derivative is going to be positive. Okay, well, so my second derivative is positive. Let's write this out neat. So since that's positive, that means h is concave up. Therefore, the tangent line in part A underestimates the temperature. Okay, you don't need to explain this picture. You don't need to draw this. This is personal. This is like a thing to help you remember which way it works. It's a math fact. It's a calculus fact that if it's concave up, tangent line under approximates. Okay, so you just can say that. Cool. Okay, last part C. There was only 3 parts. It says we got an alternative model for the internal temperature. Some function g. They give us a new differential equation here. Same initial condition. Okay. And they want us to find an expression for g of t. Oh wait, they only gave us the derivative and they want the original function. They're finally asking us to solve a differential equation. Okay, and then they're saying, oh, by the way, once you actually get this solution, what's the internal temperature at t equals 3? Okay, so we are actually going to solve a differential equation. Again, notice we've got all the way to part C and we haven't even solved it. So now we're going to do it. Stick with me here, stick with me, stick with me. What is the first step to solve a differential equation? Separate the variables. Yes, separate the variables. You have to separate the variables. You must separate the variables. What that means is get all the t's on one side with the dt and all the g's on one side with the dg. Okay, so I'm going to have the dt over here. I'm going to have to divide this all over here to get this. Separated the variables. Now I'm safe to integrate both sides. Okay, so I'm going to integrate both sides here. Integral of, oops, sorry, dt is just t. Integrate this side with respect to g. Remember, this is, you guys know what that means. G to the, or, g minus 27 to the negative 2/3. What's one more than negative 2/3? Positive 1/3. Going to be my exponent. But then I have to balance it with a 3 out here. And that negative is still chilling there. And then I put a plus c. Which side do I put a plus c on? It don't matter. But I only need one plus c. Remember, because otherwise it'd just be redundant. Pause right here. I put the plus c as soon as I integrate it. Now, remember that they're asking you to find not the general solution to this differential equation. They're asking you to find a particular solution. Specifically, the solution that when g is 0, or when you plug in t for 0 for t, you get out 91 for g. So I need to make that true right now and solve for the c right now. That's the good way to do this. Plug in 0 for t. Plug in 91 for g. And solve for c. Okay, so that's 64. Cube root of 64 is 4. Negative 3 times 4 is negative 12. So c is negative 12. Okay, remember, all I'm finding now is the c. So now I'm going to go back. I'm going to grab this differential equation. I now know the c is 12. So I'm going to take that. And I've solved the differential equation. The one thing they do ask me to do is they say, hey, write an expression for g of t, meaning get g by itself. So you do need to do that. They ask for g of t. Got to get the g by itself. This is just algebra. Yeah. I did it. I solved that differential equation by separating the variables. One last thing they asked me to do. Hey, based on the model, what's the internal temperature at time t equals 3? I'm going to toss in 3 for 2. And I'm going to get 54 degrees Celsius. Okay. I just want to say one thing about the scoring rubric, which I'll let you look at real quick here in case you wanted to pause and look at it. But the one thing that I really want to emphasize is if you look at part C, look at this. If you don't separate the variables, you don't get any points. You must separate the variables. How do you solve a differential equation? You separate the variables. So that's the only technique you know. You must do that. Okay. Same with the plus C part. Like, do that plus C part. You're only gonna get 2 out of 5 if you mess up that plus C part. All right. Cool. That concludes this video. Thanks for watching, guys. I missed you guys at school, and I hope that we'll get to see each other soon. I don't know when that's gonna happen, but we will. Don't worry. Talk to you later.